Hello and welcome to Ms. Ma's Grade 11 Functions class. This is 6.7, Solving Problems with Sinusoidal Functions. So we've been modeling with sinusoidal functions for a while, and this is a partial review. I just wanted to remind you that if you do have a wheel, that your radius is usually the amplitude, the axis is usually the axle, where you're mounted, and the period is the time for a rotation. Of course, we don't always have wheels, but often we'll have some sort of circle or something like that. We could also use some of our formulas. So if we read this question, Alahe is riding a Ferris wheel. She reached the top of the wheel 11 meters high, so that gives us the maximum after 10 seconds and was at the lowest point, that's the minimum, 1 meter above the ground at 55 seconds. What was her height after 78 seconds? So we're going to want to use an equation and then fill in the answer. So we know that her maximum was 11 and her minimum was 1. So we can actually use the formulas that we know from before. The amplitude is max minus min divided by 2. In this case it ends up being 5. And the axis is max plus min divided by 2, the mean, and that is 6. We also can find the period because we know that from the max to the min is half a period. So 1/2 the period is equal to 55 minus 10 because it takes her 45 seconds to get through that half period. So the period is 90 seconds. And then we can find the K value, the stretch or compression horizontally, which is going to be 360 over the period. So 360 over 90 is 4. So now we have our values, and depending which cos or sine we're going to use, we can figure out what the phase shift is. We know that this is the max, so that we would use positive cos, and then our phase shift would be 10. And here, if it's a minimum, then we can use negative cos, and our phase shift would be 55. So we'll fill it into our equation. Here our height is the y value and the time is the x value. So y is equal to amplitude 5 cos 4 x minus 10, don't forget about the brackets, plus 6, and that is our equation. Asks us what the height is after 78 seconds, so we'll just fill it into our equation. 4 times 78 minus 10 plus 6, you type into your calculator, you'll get 6.2 meters-ish. Hopefully, just make sure you are in degrees. We know we're in degrees because we use 360, but we'll be looking at radians in the next lesson. So that's our answer. We have a word problem, so we'll answer it with a word solution. Alahe is 6.2 meters high after, oops, I know how to spell, high after 78 seconds. Okay, let me just erase my typo mistake, and there we go. There's your answer. Okay, so the next one, we don't have a wheel, but we do have a flagpole. So pendulums are also sinusoidal. So this is sort of like a pendulum. The top of a flagpole sways back and forth in high winds and can be as far as 10 centimeters away from resting position, where if you go to the right of the flagpole, so you know flagpoles look like this, and then they might waver slightly back and forth. So if it goes to the right, we're going to call that positive 10 away, and to the left, we're going to call that negative 10 away. It moves back and forth 240 times every minute. If the pole is momentarily at a resting position at t equals 0 and started moving to the right, we want to determine the equation that describes the distance of the top of the pole from the resting position over time in seconds. So we know it started at the resting position, so that means that we're going to be at the axis, so in the middle. And we know that the amplitude is going to be 10 and the axis is 0. It starts at the resting position, so we're going to use positive sign, and it goes to the right, which is the positive direction, so it's positive sign, and so our phase shift will be nothing. And so now we just have to figure out what the period is. So don't get tricked because it says 240 times every minute. You're going to think, oh, 240 is the period. That doesn't even make any sense. We want to do how many minutes every one time is, right? So the period is the time per whatever it is, right? So here we're going to do, actually let's do in seconds because it's just so many. So we'll do 60 seconds for 240 times that goes. So that tells us that it takes a quarter of a second to do one back and forth. Okay? So that's our period. It's 1/4 seconds. So our K is equal to 360 over 1 over 4, which ends up being 1440. So now we can write our equation. Y is equal to 10 sine 1440x plus 0. And that is our answer for A. Next, it asks us if the wind speed decreases slightly such that the sway of the top of the pole is reduced by 20%, and assuming the period stays the same, what's the new equation of the function? So now we're only moving 20% less to the right and 20% left to the left. So it's 20% of, well, we're going to do 10 times 1 minus 0.2, so it's a reduction of 20%, which ends up being 8, so that's our new amplitude. And that's the only thing that's going to change because the period is the same, the resting position is still at 0, and we're going to assume that we're starting at the resting position. So y is equal to 8 sine 1440x. Okay, the last question, at what times in the first second is the top of the flagpole 5.5 centimeters to the right of its original resting position based on your equation in A? So we're going to be using this equation again, and we want to know when it's 5.5 centimeters to the right. So that's positive 5.5 centimeters. So we're going to set y equals 5.5. 5.5 equals 10 sine 1440x, and you guys have a lot of experience solving for x in this type of situation. So you just move it over. We're going to get 0.55 is equal to sine 1440x. And we're going to use beta, so actually 0.55 equals beta. And if you use your calculator, again, we're going to be in degrees because we used our 360 here. So make sure your calculator is in degrees. You're going to get beta equals 33 degrees. This 1440 is going to convert it into seconds for us. So in quadrant 1, I know that 1440x equals beta, so 33. And so when I divide by 1440, that's going to convert it into seconds, okay? So that gives me 0.02 seconds. And in quadrant 2, because that's also when sine is positive, 1440x is equal to 180 minus 33. So x ends up being 0.10 seconds. Okay, so that gives us the first period. If you think about how this looks, it's going to be, I know that my period is 1/4 of a second. So if I sketch that out, basically it's going to start at the top and then go up and down, up and down, up and down. In the first second, I expect to go, so this is 0.25, this is 0.5, here is 0.75, and here is 1 second. So I actually expect, if this is 5.5-ish right here, and I'm just going to choose a different color, if I go through at 5.5, I do actually expect to go through it 1, 2, 3, 4, 5, 6, 7, 8 times. So the question is, how are we going to find those answers? So I found the first one, which is 0.02, and I found the second one, which is 0.1, but how are we going to find this one? Well, if we're smart, we know that actually this from here to here is 1 period, which is 0.25. So you can use that information and solve it. So we're going to do x equals 0.02 plus 0.25, so 0.27. We're also going to add another 0.25 because that's right here, you see it. So x is equal to 0.52, and then we can go another period from here to here, and that will be another 0.25, so I add another 0.25 there. I'll get x equals 0.77. So previously what we would do is, if we had this 1440 x equals 33 and we wanted to add periods, what we'd do is we'd go, okay, 1440 x equals 33, and then we'll do 1440 x equals 33 plus 360, and then we'll do 1440 x equals 33 plus 2 times 360, and so forth, to get as many rotations as we want, or as many periods as we want. And this will work actually if you just do 360 divided by 1440, you should get 1 over 4. So that's why it works. So you can do it either way. We're just adding a period, and it's just whether or not you're dividing first. So are you doing the conversion first, or after, or do you just add the period from the actual thing? So we'll do the same with this one. I know that if I add another 0.25, I'm going to be above 1 second. It asks me for the first second. So I'm just going to do it for this side, 0.35, x equals 0.60, and x is equal to 0.85 seconds. And if I add any more 0.25s, I'm going to get out of range. So these are the answers. The flagpole is 5.5 centimeters to the right at these seconds. Okay? And you can just double check to see if that's the question, and there you go. Next and last, the center of the clock in our room is 250 centimeters above the floor, and the minute hand is 20 centimeters long. So we want to find the equation of the height of the tip of the minute hand in meters in relation to time in minutes, assuming that time 0 is 0.00000, so midnight. And so if we have a minute hand, we know that the period is going to equal 60, because that's how long a minute hand takes to go all the way around the clock. So that tells us k equals 360 over 60, which is 6. We have our center of the clock, that's the axis. So axis is 2.5 meters, because it asks me for meters. And the amplitude, remember, it's the radius, so that's the length of the hand, that's 0.2 meters. And it starts at the top, so I'm going to use positive cos with no phase shift. Okay, so I can just take all of these things and put them into my equation. Y is equal to 0.2 cos 6x plus 2.5. Okay, so that's the answer for the question. And then we're going to do A. How does the original equation change if the clock loses 5 minutes for every hour? So I think the wording is slightly ambiguous, but I did look it up on the internet to double check. Losing 5 minutes actually means that we would have a longer period, so our new period would equal 65 minutes. So we lose time on our clock, it becomes slower. So k is equal to 360 over 65, which gives us 72 over 13. And of course the axis doesn't change because the physical clock is not moving up and down. The amplitude doesn't change because the minute hand doesn't suddenly get longer or shorter. And we're going to start at the same time. So the only thing that changes, you can see, is the horizontal shift. The horizontal compression. So y equals 0.2 cos 72 over 13 x plus 2.5. So that's the only thing that's changing. Now the question asks us, what is the transformation on the equation? And you might think, oh, okay, well it's going to be a horizontal compression by 13 over 72. Wrong. That is actually incorrect. The thing that's going to happen to our original equation is different, because we don't start with just x, we're actually starting with 6x, right? So if you think of this as the y, and you think of this as the f of x, then what we're doing is we're doing y equals f of kx, because the only thing we're doing is a horizontal compression. So if I fill this in as y, 0.2 cos 72 over 13x plus 2.5, and I use this as my f of x, then I'm going to have f of kx, so I'll put a kx instead of my x. So it's going to be 0.2 cos 6 kx plus 2.5. So all the other things are the same, the 0.2 and the 2.5 and the fact that it's a cos. So basically we can say that 72 over 13 x is equal to 6kx, or in other words, 72 over 13 equals 6k. If we solve for k, we'll find that k is equal to 12 over 13. So that is the transformation that's occurring to the original equation to get to this equation. So we'll say that the transformation is a horizontal compression by 13 over 12. And that's what's going on there. Okay? And let's do the last two. How does the original equation change if we're using the second hand? So we know that the second hand is about the same length, well, it's exactly the same length as the minute hand in most North American clocks, and that's true in our classroom clock. So the amplitude is still going to be 0.2, but the only thing, and of course the clock is mounted at the same spot, so the axis is still 2.5. The only thing that's going to change is the period. It takes 1 minute for the second hand to go around the clock, so be aware of the units when you're doing the question. That tells us that k is equal to 360 over 1, which is 360. So the equation is going to change. It's going to become y equals 0.2 cos 360 x plus 2.5. If we do the same hocus pocus as we did here, we'll know that 360 is equal to 6k. In this I'm finding the transformation, so k is equal to 60. So the transformation or horizontal compression by 1 over 60, because we can fit 60 seconds into 1 minute, right? So we're going to get lots and lots of little periods where the minute hand would have one long one. And so the last question asks us, how does the original equation change if time 0 is when the minute hand is pointing at the 3? What is the transformation on the equation? So if you think about that minute hand pointing at the 3, and it's the minute hand, so okay, so that's pointing to the 3. We're using positive cos again because we want to know what the transformations are. We're actually going to have, and actually, you know what, it's easiest to graph this out. So let's do a little graph. Okay, so the original equation, I'm just drawing my 3 things. I'm going to do it in red. So my original equation starts at the top and it goes like this. Okay. So my new equation is going to start in the middle at the 3, and it's going to go downwards because at the 3 it goes down. So it's like this. Okay, so what did we do to this equation to make it look like this? Well, we moved it to the left by 15. So my equation is going to be 0.2 cos 6 x plus 15. I'm moving to left, plus 2.5, and the transformation was left 15. Okay, 15 minutes because at the 3, that's 15 minutes away from the top, and that's the answer. So thanks for watching. I hope that you enjoyed it. Bring me any questions you have to class. If you found any errors, then put them in the comments below, and I will see you soon. Thanks.